to the Computational Chemistry and Material Science mini symposium at JuliaCon. And the next speaker is Lukas Weber from Center for Computational Quantum Physics, Flatiron Institute, New York City. Talking about Carlo.jl, high performance Monte Carlo simulations in Julia. Please, floor is yours, Lukas.
Hello everyone, I'm Lukas. Today I want to talk to you about this little package, Carlo.jl, which is a framework for high-performance Monte Carlo computations in Julia. First of all, let's start with the question, what is Monte Carlo? In Monte Carlo, the idea is that you want to solve a high-dimensional sum or integral by using random numbers. So imagine you have a function f that you're integrating over, and then if you can write that function as a product of another function g times a probability distribution p, then you can reinterpret this problem as a sampling problem, sample from this probability distribution, do the statistical average, and solve your integral that way. In practice, the way we sample these probability distributions is using a Markov chain. So we pick some starting point x, and then we keep doing random updates in a certain way that converges to the target distribution after some time. And if we do this for long enough, we get this Monte Carlo time series, which is autocorrelated, but if you do a time average, you arrive at something that converges to the correct result for the integral. The statistical uncertainty of this average is scaled then as 1 over square root of the number of samples, which in low dimensions is pretty bad, so please never do this for 1D integral. But in high dimensions, this doesn't actually depend on the dimension, so it becomes a really powerful method. And this is exactly what makes Monte Carlo, or what we call quantum Monte Carlo methods, so popular in condensed matter physics, where we're interested in sampling objects like the quantum partition function or the many-body wave function. The slight problem here, however, is that these objects, either they don't have a straightforward interpretation in terms of a probability distribution, or that interpretation is just very hard to evaluate. You cannot calculate the weights of the distribution. So what you need to do first is you need to find a mapping which might not always exist, and if it exists, it depends on the system. And this mapping then maps your complicated quantum object into a classical probability distribution, which can be can either be a discrete or continuous or both. And this probability distribution then lives typically in a very large configuration space that's even larger than the Hilbert space that you started with. But high dimensions in Monte Carlo is not such a big issue as we learned, so we can just eat this, and as long as we can sample this distribution, we can use it to understand our system. Sampling this then requires another set of system-specific tools that we can use, and then we carry all of this out, and out comes a whole lot of data, so order of terabytes it can be. And this data you take, do statistical post-processing, extract averages and expectation and error bars for your quantities of interest, and then you're done. So if you look at this whole program, you can divide it into two parts. One is the system-specific part, which I call the fun science, where really you drive the field forward by innovating new methods and trying to optimize your algorithm. And the rest is basically the bookkeeping that always stays the same. But since these problems tend to be such large-scale problems, you really want to do this in parallel. You want to do the sampling in parallel, and if possible, it's also nice to have a workflow that prevents errors and maybe is understandable to another person as well. And the desire to have all of this at once sort of is the reason for Carlo to exist. So Carlo is a framework that allows you to write these kind of simulations, and it takes care of the bookkeeping for you. So you get a Monte Carlo-aware MPI scheduling of your sampling. So you can give it a number of machines, and they will collect samples in parallel across different parameter sets, you name it. And the second thing it does, it takes care of your input and output files and provides a checkpointing facility. So if something goes terribly wrong, you run overtime with your very long simulation, is fine. You can just restart it from the point where you left off without losing much progress. And then what it does is binning, analysis, and jackknifing, which are the techniques that we use for the statistical processing to get our results from the sampling. And for Monte Carlo experts, the idea is that they can focus on the fun part, quickly develop a new method, and then get all of these bookkeeping things for free to get basically a production-ready code out of it. And the hope for non-expert users is that, okay, if we provide this unified interface, this makes existing codes easier to use and makes Monte Carlo methods more accessible to the general public, maybe. And these two viewpoints are exactly what I want to structure the rest of the talk about. So I showcase first, in the first part, how to implement a simulation code. We're going to do a very simple model. And then in the second part, I put on my user hat and I show you how to run a pre-existing code that is built on Carlo. So starting with the first part, what we're going to implement is a simulation of the easing model. So imagine we have a magnet that lives on a square lattice, and on each of the sides there's a spin that can either point up or down, which is modeled by this variable sigma, which can be either +1 or -1. The interactions of the model are then along the nearest neighbor bonds of the lattice, and the distribution we're interested in is the Boltzmann distribution of the system. And to simulate this model using Monte Carlo, there's three basic things we need to do. First, we need to choose some initial spin configuration. Then we need to implement the Monte Carlo update, which takes us from one configuration to the next in a way that fulfills detailed balance and converts us to the Boltzmann distribution. And then we need to implement observables like demagnetization that can teach us something about the state of the system. Implementing these things in Carlo works by implementing this abstract Monte Carlo interface, which we just subtype here. And for the easing model, what we need to store is just the temperature of the system and a matrix that stores the Monte Carlo configuration, all the spin states on the lattice, which we just do a matrix of integers here. And then all the rest is implementing methods that act on this type somehow. Starting with the construction and initialization. So first thing we need to realize here is there's actually two kinds of initialization. The first one is the constructor, which is called each time a simulation is started or restarted from a checkpoint. So the task here is just to set the parameters and set up our data structures, but not doing anything physical or setting up any spin configurations. So that's what we do here. The parameters, that's this a dictionary we get passed as an argument, contains input parameters that come in from an input file that we will see later. So here we get the system size and the temperature, and then we allocate a matrix. Then the second function, this Carlo.init, is the one that's really only called when the simulation is started, and there's where we set our spins to some random numbers. One little detail here is, additionally, we get this Carlo Monte Carlo context pass, this CTX. And whenever we want to use a random number in Carlo, we should use this ctx.rng, and by doing this, our results become reproducible. We can set a seed in the config file, and then everything stays the same. So that's the initialization. The next part is the heart of the algorithm, basically. Is the Monte Carlo update. And for the easing model, there's a bunch of different choices you could have. We just take one of the simplest ones, which is the Metropolis update. And that works like this. We just choose one side at random, and then we flip it with a probability that's related to the energy difference such a spin flip would cause. And then the Carlo function we need to implement for this is Carlo.sweep, and sweep is basically a Monte Carlo jargon for do enough updates so that you significantly change the configuration. So we we repeat this metropolis update for as many times as there's number of spins in the lattice. And you see here, choose a random site, calculate the energy difference, and if we have to, we flip the spin. Yeah, that's the sampling done, okay. And now measuring observables works, we focus just on the magnetization and the spin-spin correlation function here to keep it simple. There's this function Carlo.measure, where you do the measurements of your observables, and for the magnetization, we just do the average of the spins over the lattice, and the correlation function. You could do many fancy things using symmetries here, but the simplest way is just look at the correlation function in the x direction and average over the y direction. And lastly, we need to take these things we calculated and call this function measure on the context, and that will save one sample in the time series, basically. So we were interested in the second and fourth moment of the magnetization, and for the spin correlation. One note here: these observables, they can be either scalars like the magnetization moments here, but they can also be vectors or arbitrarily shaped arrays like the correlation function. So this is the main thing, and now there's some features that may be not so obvious. So if we have these averages, sometimes we're interested in nonlinear combinations of them. Take, for example, this Binder ratio here, which is defined as a ratio of moments of the magnetization, so m squared divided by m to the fourth. And this guy, our basic statistics tells us if we just plug in the averages in this nonlinear function, and there's some error bars, we get a bias, right? And this bias can be pretty significant because imagine you have some disordered magnet, then this distribution of the magnetization moment can be actually squeezed against zero and quite non-Gaussian. So it's important that we have something to correct any biases and also get the correct error bar. But yeah, Carlo has your back on this. There's this facility called evaluables. You have this register evaluable function where you can define functions of the observables and get an, Carlo will do jackknifing and correct the bias and give you the correct error bars for this one. Now there's only one last thing, I promise. For the checkpointing, Carlo uses HDF5, so it expects you to implement these two functions. Write checkpoint and read checkpoint, I just save and read the Monte Carlo configuration from an HDF5 group. This is, for just a spin array is a simple thing. And then we're done, our simulation is implemented. And now the reward for going through this implementation part of the talk is we get to run some simulations now. Let's start with the easing code that we just implemented. So the way Carlo is structured is it's meant to be used with MPI. So the whole recommended workflow is to write a job script that you can then later run with MPI run. And that works like this. You start by importing Carlo and Carlo job tools, and then this easing code, imagine everything we just wrote is in a module called easing. Import that as well. And then we want to set the parameters of a simulation. And we want to set not only just one simulation, but a bunch of simulations that Carlo then can parallelly schedule with work sharing and so on. And the way to do this is using this task maker thing tool that's defined in the job tools. And the task maker, each property of the task maker is a parameter in the simulation. So we start with these three properties, sweeps, thermalization, and bin size. They are Carlo internal, and they're the same for every code that's built on Carlo. The sweeps are just the number of updates you want to do in your simulation. The thermalization is the updates you want to do at the beginning of the simulation without taking any measurements, because remember, these Monte Carlo Markov chains, they need some time to thermalize to get to the right target distribution. And then the last thing here, bin size, that is how many samples of your observables are averaged before you write to disk. This is a pure memory and bandwidth saving feature, not related to the statistical post-processing that happens after the simulation, which also does binning. So you can choose whatever you want here. The results will be the same. You just should choose so many that your disk isn't full, and so not too many, so that you still have some bins left on your disk that you can do the post-processing on. And then we set the system parameters. So our goal here is to do simulations for a bunch of different lattice sizes and also a bunch of different temperatures. And the way this works with the task maker is that each time you call this function task, it creates one snapshot of all of its parameters that you've set. So we call this, we go through this loop, we set the temperature and the system size at each iteration and then call task. Yeah, I found this way of programming your job file or your parameter sets pretty handy, especially in the case where you have something more complicated that nested loops. Like if you have a very let's say you have another thing that gives you a data frame of certain parameters, you want to get them, you want to pre-process, filter them before you put them into your job file, then you can program all of that and make your parameter set that way. Now let's say we are done with that, and then we put everything in this job info structure. Yeah, the first argument is the job name or the directory where we want to save all the simulation data at. The second parameter is the type of the subtype of abstract MC that we implemented in the first part of the talk. Then the runtime is the maximum time the simulation will run for. So if you set a large number of sweeps and you cannot finish within the runtime, it will just go until the runtime and then say, okay, I give up, I save everything, I save a checkpoint, you can restart me with more runtime later. The checkpoint time is the time interval between saving checkpoints. And then the tasks is the number of parameter sets. So if you don't like the task maker, so make tasks takes the task maker and spits out an array of task info objects. If you don't like the task maker, you can also build the array in your own way and put it in there. And then start is what starts a command line interface that you can then use from your console. So that's the job script. Let's run it. And yeah, I run it with MPI run or srun on your cluster. And with a given number of cores, Julia, then the example job.jl, where we wrote this stuff from the last slide, and then the argument starts the simulation. There's also a bunch of other features in the CLI which you can explore with --help. For example, you have a feature like status that shows you the status of an ongoing simulation. Or my favorite feature for impatient people, you can collect data that's already there from incomplete simulation. So if you're impatient, you can just check what's already there and test if your post-processing pipeline is working and stuff like that. But let's just assume we're all patient here and we waited until this is over. And then our results got saved. And then Carlo has a little tool that allows you to extract the data that it spits out, which is all of the statistically post-processed results are in the JSON file that is called like this. And then you call this data frame method here, and you get a data frame. The columns of this data frame are all of the parameters of your job and also all of the observables and these evaluables that we defined. For example, here the binder ratio, and then I can plot them, and I see something like this. Yeah, remember the binder ratio was the strange ratio of magnetization moments, m² divided by m to the fourth. Here as a function of temperature. And the binder ratio is defined in such a way that it has a crossing at different system sizes when there's a critical point. So we see here for the easing model at around 2.269 or something, we expect the critical temperature, and that pretty much fits with this, this crossing that we see in the curves. Yeah, so that's great. But of course, I don't want to let you out of here with just the easing model. There's a little extra, treat. We're also going to look at StochasticSeriesExpansion.jl, which is a state-of-the-art quantum Monte Carlo code for spin system that's built on Carlo and available for you right now. It has a lot of knobs where you can generalize it to a lot of different systems, but one thing that's implemented out of the box is this anisotropic Heisenberg model with this Hamiltonian. And since we're in the chemistry and materials section, I feel obliged that we should calculate something for actual material. So there's this anisotropic honeycomb magnet, barium nickel vanadate. It's a spin 1 magnet, and there's a simplified Heisenberg model description of it, where you just take the nearest neighbor honeycomb exchange coupling, and this single ion anisotropy and the easy plane single ion anisotropy term, DZ. Set them to those values, and then let's put it in a job script. It's a bit more complicated for the easing than for the easing model, because this code has a lot of more features. So we say we want to have this magnetic Hamiltonian that we saw. This the magnet model set spin equal 1. It also supports arbitrary spin on arbitrary lattice size, but let's skip that for now. The lattice should be a honeycomb lattice, and the size is 40 by 40 unit cells, which actually you need in this case because the model has some long-range magnetic correlations at low temperatures. Then the exchange coupling and the anisotropy from the paper. One thing for numerics, I think, is always good to work in the natural units of the problem. Also, I see as a typo that should. No, it's not a typo. I rescaled everything in terms of units of the exchange coupling. But that's okay. And then we want to simulate a bunch of different temperatures. So I do just this one loop over temperature here. Put it all into the job info and start. This, with a 40 by 40, it takes a bit longer to run. But once you have that, you can compare it to the experimental data, which is the black curve. And then the blue is a QMC plus a constant, which is a diamagnetic contribution that's not captured by this Heisenberg model. And you see it fits rather well, except for low temperatures. And this low temperatures, probably there's some other, the simplified model is not quite enough. Probably there's some next nearest neighbor exchange couplings or something else that becomes important. But I think it's a handy tool in case you're an experimentalist and you like to check the model parameters you got from some other place. You can try to use this code. And with this, I'd like to conclude. Carlo.jl and StochasticSeriesExpansion.jl are available for you as registered packages. There is documentation which describes a few more advanced features like non-trivial parallelism. So far, we've only seen the trivial, embarrassing parallelism of Monte Carlo simulations. You can always collect in parallel, right? But Carlo also lets you define parallelism within the sweeps and measurements themselves, if you want that. There's a parallel temperament feature, and for stochastic series expansion, all these ways to expand the Hamiltonian that you want to study. And then there's, apart from the documentation, there's the Cyphos physics code basis, which is available and has some explanations on the inner workings and benchmarks. And if any of this made you curious and you want to, or you're building something with it, you can always let me know. And if you run into issues, I'm happy to help. Thank you for your attention.
We have time for a few questions.
Hi, thanks for the nice overview. So I'm wondering how I should think about this sweep step. Can I also think of it as just a single step in my Markov chain? So
Yes.
here you said that you had to take an efficient number of steps or sufficient number of steps, but I guess that was just your model. But if I have a model where I don't like to do that, that's also fine.
Yeah, this reminds me a little bit of the keynote this morning. When I wrote this code, I was following the jargon of my field, where the sweep is like some way to just say update. So if I had written it again, probably I would just call it update. But basically, think of it as the update in your the step in your Markov chain. It doesn't really matter as long as it's. Yeah, the reason I repeat the spin there is because if I want to scale up my system, I repeat the Metropolis update is if I want to scale up my system, I want the update not to be less efficient with increasing system size, right? So you can just put whatever you want, basically.
Okay, thanks.
Yeah. Yeah.
Apologies if I missed this during at some point during your presentation, but are you running multiple Markov chains per thread? Because one reason I mentioned this is because with how Julia's base rand call works, if you are using that, it goes faster if you are calling multiple, if you're asking for multiple values at a time. Because it can pull, I believe, 8 in parallel for floats, I think. And you could see maybe, I think, around a 4 times speed up, I think, if you're doing 8 chains at a time on each thread.
So in this case, the parallelization is MPI, so only one thread, but yeah. So if I have only one thread, I should get random numbers in parallel, you're saying?
Yeah, I think you could, basically instead of getting one random number at a time, you could be getting maybe 8 at a time, and I think you would see a speed up.
I see.
Yeah.
So yeah, I hadn't thought about that, but the thing is, usually so for these things, often the random number generation isn't actually the bottleneck. You're either doing some linear algebra that's also pretty expensive on the side, or you are jumping around a big array and have some memory bottleneck. But
yeah,
it's
that's true.
interesting to think about the cases of random numbers. Yeah.
Any more questions?
Yeah, I have a quick question. You store your spins in a matrix of 8-bit integers.
Yes.
But can they just be stored in the single integer that 0 is spin up and 1 is spin down, and that will shrink your memory usage by quite a bit?
Yeah, you can optimize this quite a bit further. Just for the sake of the presentation, I went with the simplest way.
All right, let's thank the speaker again.
Yeah.